this crowd, but have teenagers, and I fall into both those categories, realize that the internet has changed not only how we do science, how we do research, how we do business, but also how we interact socially. So the internet has just had an amazing and profound influence on our global culture, and this is one of these complex systems I think that would be of interest. Now, one of the aspects of this is, if we've got a quarter of the world that is wired, what are the implications of the rest of the 3/4 of the world? If we further expand the internet, or we think about having more and more content on the internet, what is the implications of that? And one aspect of this is energy usage. If you consider the amount of electricity that's required to drive servers that operate as the nodes of the internet, roughly about 1% of electricity in the world is devoted to this. So in the United States, this is something on the order of 1,000 megawatt power plants, which means coal burning plants, and it's something on the order of 14. So if you then think about just at the current level of usage, if we're going to triple this in order to get to the rest of the world, this has a huge implication in terms of energy usage. So the question is, can we keep adding these sort of power plants to support this infrastructure? And probably our children or grandchildren will say, no, we can't. So what that tells us is that we can't continue to do our systems, at least the hardware side of things, the way we've been doing them. So what I'd like to talk about is some of the things that we're looking at in my group for making digital laser sources for that would be using the internet, that would use to take less energy. And so I'm going to talk a little bit as an introduction for VCSELs. I know there's been some work by Professor San Miguel here in the past on VCSELs, but I'll say a little bit about that. And then I want to introduce what I'm calling mode modulation techniques, a way to decouple the modulation bandwidth of a laser from its required energy. And I'll actually show you a couple examples here, a little bit about the coherent array work, and then a lot more about the push-pull modulation. And I will try to finish by 10:20, so we're on schedule. So a VCSEL vertical cavity surface emitting laser is shown here. And I presume that many of you are physics students. So this is a microcavity laser. We have two mirrors that are separated by essentially one wavelength. So that's why we call it a microcavity laser. This is a TEM, a transmission electron micrograph, showing you the one-wave active region, and you can just maybe there's 5 quantum wells there, which I can see on this screen. And then we have two mirrors. The light is emitted out of the top. These were devices that were invented in Japan in the late 70s, 1978, 79. There were a lot of development in the United States, Europe, and Japan in the 80s. And by the mid-90s, this turned into technology. And there are now about 10 million VCSELs manufactured a month. There's been 100 million deployed in the internet, and approximately nearing 1 billion VCSELs that have been deployed globally, if you include laser mice. Laser mice has been a giant number. So there's a lot of these lasers out there. What I want to focus on is what was the first killer application of this technology, which was in optical communication. And VCSELs, as I mentioned, are used in local area networks. Anything where you want to transmit large amounts of information over about 100 meters. That VCSEL is the thing. So connecting computers, connecting switches within data centers. If you have a really high speed and high resolution printers now, you get an optical cable between your computer and your printer to drive that. That's an internet. That's a VCSEL. HDTV is one of the big new drivers for VCSELs, because obviously there's a lot of bandwidth that needs to be transmitted to the television, and at least in the United States, we want to put our televisions, high definition televisions, on one wall, and our computer, 10 meters away. You can't do that with a copper cable. You have to do it with an optical connection. So so local area networks are becoming important, and then there's a belief that this will actually go into the board and perhaps even intra-chip. So a fiber optic link, very simply, is a piece of optical fiber We have a laser on one end and a detector on the other. And we put digital signal in, and we're going to modulate essentially the amplitude, the light intensity of the laser, and detect that at the photodetector. And the beauty of this is that we have very little loss in the fiber, and we can operate these lasers at very high speed. In the VCSEL world, 10 gigabit or transmitting 10 gigabit per second is now becoming very common, and we're looking at 20 gigabit and even 40 gigabit systems. In the long haul, if we're talking about a connection between here and the mainland, that would be on a long haul fiber that would use a bigger laser, but they're going to have multiple colors of light going through these fibers. VCSELs are at the moment just one wavelength. So from an electrical engineering point of view, the way we use these lasers is we have current input and light output. So we have the Li characteristic here. So we're going to have a digital signal coming in at some bias level. So we're going to have some DC current with a variation. And then, of course, this is then transferred into a light output, a digital light output. Now, if we were to characterize this laser source and we wanted to see how fast it operates, we would do what's known as small signal modulation. We would, for a fixed amplitude here, we would vary the frequency, and we look at the output intensity, and we divide the output by the input. That would be the so-called modulation response. So if it's 1 to 1, we have on a decibel scale we have 0, and then what we talk about is that as we increase the frequency, at some point the output can't follow the input, and it'll fall. And at the point at 3 dB or 50% decrease in this output amplitude, we call it the 3 dB bandwidth. 3 dB bandwidth, and in this particular case, this is for a high-speed VCSEL where we have about a 15 gigahertz modulation bandwidth. Now, the point is that you'll notice that there's a peak here that we see in this response, and that comes about from what's known as a relaxation oscillation frequency. So in the semiconductor laser, we have a population of carriers, we have a population of photons. These two populations are coupled. So anytime they're coupled together, there's typically a resonance between these. And that's the trick that we use, is that this resonance frequency, we try to push it to as large a frequency as possible in order to push this 3 dB point to as large a frequency as possible. If you look at that frequency, at this relaxation oscillation frequency, it scales with the essentially number of photons above threshold. So in order to make a laser faster, to modulate faster, we have to drive it higher and higher above threshold. What that means is, to make a laser go faster, we have to use more power. So, or I should say, driving a laser higher means greater photon density. So what this means specifically is, the faster the laser, the more power it consumes. And this is shown here very explicitly. This is my grad student, Chin Chin, who actually did most of this research I'll show you. This is the data rate of a VCSEL, actually a very optimized VCSEL as a function of operation power. And you can see that basically you want to go at higher speeds, you want to go to 25 gigabit per second, that means you're going to have to operate this at higher power. So if we want to expand the internet, we either have to use more lasers, which means more power, or we use existing lasers and we operate them faster, that still means more power. So the point is, higher bandwidth following this approach implies more power. So we need to somehow decouple the bandwidth from the photon density. And that's what I'd like to talk about. So, I don't know what happened to my, so the way to do this is, well, there's 3 ways that we're looking at to do this in our group. And I call these, in general, mode modulation techniques. And the idea is that instead of modulating the amplitude of the laser, what we want to do is we want to modulate the mode of the laser. And this is a bit of an oxymoron, because a mode is essentially a solution to Maxwell's equation that doesn't change the time. So what I really am saying is I want to change the boundary conditions of Maxwell's equations within the cavity such that if I stand and look at the output of the laser, it looks like I have a varying amplitude. So there's 3 ways I'll talk about. I'll say a little bit about polarization modulation. This has actually been done for a long time in VCSELs, but we're re-looking at it. And I'll say very little about that. I'll say a little bit more about spatial modulation using coherent pixel arrays, and then the area that we've done the most work on is push-pull longitudinal mode modulation in a composite resonant vertical cavity laser. So just a little bit of polarization modulation. The polarization of a VCSEL is very rich physics. There's been some pioneering work here. There's a whole model that Professor San Miguel developed to describe this. The point is that we can have one transverse mode of the laser, but we can change its polarization. And therein lies the possibility of using that as a way of modulation. This is showing you the light output as a function of current, and you can see that at a certain current level there's a change in the polarization. And in this case, this is happening sort of naturally, and this has been investigated by many researchers. The idea is that if you can modulate through this transition, you can put information on the change of polarization. What we're interested in doing is to no longer rely on these natural transitions, which turn out to be rather slow, but to force the laser to change its polarization. And so we're pursuing device structures, and at this point we're just designing masks, we're just designing the devices to do this. But the idea is that we want to force the laser to change the modulation. And the beauty of this is then that this is independent of the photon density, that we can bias the device at any current level we care to and change the polarization, at least in principle. So this would be a way to decouple from the modulation rate from the power, if we can make this happen fast enough. So there's so I won't say much more about that because we haven't. We're just working on these designs. The second thing I'd like to talk about, though, is what I call spatial modulation, and this relies on the use of in-phase coupled VCSEL arrays. So I wanted to give you just a little bit of background on this. Again, this is, if you want to talk about complex systems, one VCSEL is fun, but now you take multiple VCSELs and you put them together laterally and they couple together, then you have a complex system, at least in my opinion. And so we have a lot of phenomena, most of it bad, or at least most of it not useful. But so what we're trying to do is we're trying to make useful phenomena. So one of the things about a coupled array is that when you have multiple sources, I'm showing you here, this is some early work done at St. Denis National Labs, right when I began there, where you see multiple emitters here, and all these emitters emit, and they couple together laterally. Unfortunately, as I'll show you in just a moment, there's a gap between all these emitters, and so in general, the wave function wants to go to zero between the devices, and that just naturally makes these things want to emit out of phase, which is a problem. And I'll show you that in just a moment, but one thing you can do to fix that is you can put phase shifters on here, and that's why you see every other device here a little bit thicker. Very complicated approach, but you can build in-phase arrays. You can also use the Keymode Coupling, which I won't say too much about, other than to say that it's a very complicated way to, the fabrication is very complex, but it has led to some very nice results. This is some work done at the University of Wisconsin, where I think they made as large as 10 by 10 arrays to make in-phase devices. So what does in-phase mean? I'm showing you here a 2 by 2 array. So each of these squares represents a laser. And in this case, if each of the phase of the elements is, each element is in phase with each other, then if you look in the far field, what you would see is a lobe on axis with a central maximum. So this is a false pillar image here, and this central lobe is basically the superposition, the coherent superposition of all four of these emitters, such that you've got an on-phase maximum. That's kind of what you'd like, and an important thing about this is that this central lobe can be much narrower than an individual element, and that's what coherence gives you. Now, this is what you'd like, but what you typically get is the out-of-phase mode. And the reason is, and then in this case, each of the elements are 180 degrees out of phase. And the reason for that is that we have some sort of discontinuity between the elements, whether that's an etch or something. And so the wave function goes to zero. Here you can see that the wave function is finite. So the wave function goes to zero because this is a plus and this is minus. So the 180 degrees of phase. What that gives you in the far field is this 4 lobe. far field, where on axis you have actually a null. And so from the point of view of a useful laser, this is a problem. What you'd like is that. What I'm going to talk about is how we can build in-phase devices, which are the ones that are more difficult to make. And the approach that we take turned out to be very simple, almost embarrassingly simple. And that is that we combined ideas of photonic crystal cavities with ion implantation. What I mean by that is the following. We introduce photonic crystal defect arrays. And so we take a perfectly good VCSEL, actually a broad area VCSEL, and we introduce into its top facet a series of holes, a photonic crystal pattern. And we leave out a couple of holes and we form a defect. And so what will happen is this device will define 4 cavities. And the cavities can be coupled because we can control the holes that connect these various cavities and control the coupling. So this photonic crystal pattern, holes that we etch into the top mirror, actually define the optical cavity. And then we can combine, so we define the cavity, we control the coupling, but unfortunately this structure tends to emit out of phase because we have a discontinuity between the elements. There's a hole here. So basically the wave function wants to go to 0 there. So that'll give us this out of phase condition. But what we can do is we can combine that with an ion implantation. What we can do is we introduce a way to electrically isolate these 4 cavities from each other using essentially destroying the semiconductor through ion implantation. So the idea is that through two fabrication approaches, an ion implantation to define the electrical cavity and etching to define the optical cavity, we can create a coupled array where we define the gain distribution, we can control the coupling, and we inherently get in-phase operation. And that's the key to this work. So this is again a side view of a VCSEL. Okay, the top mirror, the bottom mirror. I'm sorry that this is. I thought this was color, but I must have the wrong slide. What I'm showing you here is this region here represents the ion implantation. So when we inject carriers from this top contact and bottom contact, they'll tend to be funneled in the central region. So we have a fairly broad area of gain. On top of that, we've introduced this photonic crystal, which then defines the optical cavity. And so this is what it looks like from the top. And you can just make out there's a couple of holes here which define the array. When we fire up and put current in that, then we get this 2x2 array. And what you'll notice is that there are these fringing fields between the elements. That is a sign of coherence, that we're actually coupling between these elements and giving us a coherent array. And the result is, in the far field, we see an in-phase mode. So this is the light versus current characteristics. This is the spectral characteristics. And so you can see that over this entire operating range, even though there's a couple of discontinuities here, that we see a single mode. So this is a couple. We don't have 4 lasers operating independently of each other, because if we did, we'd have probably 4 spectrum sitting either very close or on top of each other, giving us a wide spectrum. We have one super mode locked together, and then for the aficionados, if we look at the polarization of this is all one single polarization. This is one polarization, this is the other. It's all locked in one polarization and one fundamental mode. And this is what the far field looks like. At low current, we see a central axis here, and as we drag it harder and harder, we find that we have this in-phase mode, and this in-phase mode has about a 2.6 degree divergence. So this is much smaller than the divergence from an individual element, and we get lots of power in the central mode. Okay, now, so far, this has nothing to do with modulation. What's interesting about this is this is the in-phase mode. We have the out-of-phase mode. It turns out that this was a surprise to me, is that you have all the possibilities in between. So you can actually you can beam steer these arrays. And I'm showing that here with a 1x2 array, I have two individual lasers. They're locked together. They're coupled, but I have two independent current injection. So I can change the current to each cavity. I can change the phase, the relative phase between the cavities. What that allows me to do is it allows me to change the angular position of that central axis, and I can beam steer. So you can see here, in this case, over a 1 milliamps variation, this is on a 25 degree. This is the far field, and this is 25 and 25 degrees off of normal. And you can see that I'm changing from, in this case, about 3 degrees on the left to 3 degrees on the right. So I got about a 6 degree angular change in that far field. And so the idea that we're working on, again, is to build arrays in which we can have an angular variation in the output. This would then be incident on a photodetector, and the idea is that we switch it on and off. Whoops, too many times. For digital modulation. So again, this would be independent of the drive. We can bias these lasers at any point, and then a small change in current would give us modulation to decouple the modulation rate. Now, whether or not this process, we think this process is electronic from the things that we've studied in terms of this tuning, so we think this can be very fast. So that's these two approaches. The last approach that I'll talk about is push-pull modulation. This is the least speculative. This is an approach that we have demonstrated modulation. And again, it talks about, it relies on coupled cavities, which fits into complex systems. So let me introduce this device. This is what we call a composite resonator vertical cavity laser. And the idea is that instead of having two mirrors with one active region, we actually have two active regions and three mirrors. So these are two coupled lasers sitting on top of each other. In this case, this is the refractive index variation through the cavity. So you can see through the device, see the two cavities here, and you can see the modulation of the standing wave in the longitudinal mode. And this is the overall envelope. And so you can see that it's maximum maintenance of two cavities. Now what we can do is we can, again, this is a one optical mode, but we introduce independent current injection. So we can introduce different amounts of gain into each of the cavities, and thus we can change the device characteristics. So from an electrical engineering point of view, we have a ground signal ground configuration here so that we can do very high speed modulation of this device. It turns out that this is looking down from the top view of these devices. This device structure requires about 13 levels of photolithography. It's one of the most sophisticated devices we've ever tried to build in an academic clean room, and it was I was very impressed that hard-working students can do such a thing. Now, it turns out that you can do lots of things with these devices, and one of the things that's very interesting is that this is actually a way to introduce much more functionality to the laser, which again leads to power conservation. But I'm really not going to talk about any of these other things. I just really want to talk about the push-pull modulation. First of all, these lasers can be very fast. I'm showing you here, again, small signal modulation characteristics, and you can see that these devices, we can drive them to over 20 gigahertz. So this is near a record for pixels. And the reason is that because we have two cavities, we can carefully tune their characteristics such that they can modulate very, very fast. But what I'd like, but that's using the conventional amplitude modulation, where I'm turning the laser on and off, which, even though it's very fast, it's still requiring more and more power to get to the modulation bandwidths. So what I'd like to try to see if there's a way to modulate this laser without, independent of the photon density in the cavity. And that's what gives rise to the idea of push-pull modulation. And what we want to do here is we're going to vary the current into each cavity, but we're going to do it out of phase with each other. So when we inject carriers into one cavity, we're extracting the same number from the other cavity, and vice versa. So the net total carrier concentration photon density in the cavity remains constant, but we are varying where the carriers are in the two electrical cavities. This essentially gives rise to modulation. I'm showing you here these wave functions again. This is in the case where the top cavity, the cavity closest to the output side of the device, has a little more carriers injected into it. Thus, the refractive index is depressed, it's reduced, so effectively we have a shorter cavity. What that does is that the wave function tends to slosh into the top of the device, and we'll have, and I'll show you in just a moment, a little more light coming out. When I reverse that and I inject the carriers in the bottom cavity, extracting an equal number out of the top, then the mode is sloshing back into the substrate. So what I'm doing here is I'm changing the longitudinal mode of the device. And by doing that, I effectively am modulating the output. That if I look at what's coming out of the top of the laser, that I see here this looks like a very small change, and it is relative to the total field, but this is about a 3 dB change in the light output. And so what I'm basically doing, again, I'm either throwing a light into the substrate or throwing a light out of the top. But I'm doing that at a constant photon density. So the idea is that this is independent of the bias level. So you can do rate equation analysis, and I throw this up here just to show you that I can write down equations. But this is absolutely wrong. And the reason why it's wrong is if you think about it, rate equations where you link the carrier concentration to the photon concentration. I'm telling you the net number of carriers is constant, the net number of photons is constant. So you should see nothing, and that's in fact that's the case. The red curve here corresponds to the typical modulation of a laser. We modulate the carrier concentration, but when we do this push-pull, it's a flat line because nothing's changing. So we have to modify these curves. We have to modify these equations, and so this is absolutely incorrect. But you know, I'm an engineer, so I can do something to approximate this. So what I do is I just tag on a little thing on the end to represent this modulation, and then basically, take a step back here. You know, my current that's being injected is out of phase in the two cavities. So when I have exactly 100 degrees out of phase, and I can represent that with, here we go. I can look at the variation in terms of amplitude in that phase. What happens when I add in this extra part, I can look at this modulation, and what I see is that, again, the red curve here corresponds to the conventional modulation. These other curves correspond to push-pull modulation. And when I introduce this ad hoc term, I can look at the stability against amplitude variations and phase variations. And what I find is it's pretty robust. I mean, these are modulation rates that are very exciting, and there is very little net change in the carrier concentration. So I'm doing this independent of the power. So here is the device structure. So we built. It's hard to see here, but this is a 2 mesa structure with lots of contacts and Pauling unit. We do all the tricks we can to make very high-speed devices from an engineering point of view. And we have 2 separate signals that we can put in to these cavities so that we can inject carriers into one or the other cavity. Now, it turns out there's always the idea, I can draw great pictures, but when I actually make the device, that's when real life comes in and makes things complicated. It turns out that the 2 cavities are not identical because of the way in which we fabricate them. The bottom cavity is an oxide confined cavity, and the top cavity is implanted. From the point of view of today, all that says is that the 2 cavities have different cross-section areas. So I want to have the same current density, but it takes different currents to achieve this condition, and it's not clear what it is a priori. So we have to figure out a way to calibrate this. So the way we do that is we use the noise characteristics. If you take a semiconductor laser, you bias it DC, and you look at the relative intensity noise. You look at the output as a function of time, and you do a power spectrum analysis of that noise. What you find is that there's a peak in the noise. And that peak corresponds to this relaxation oscillation frequency. At the frequency where the carriers and the photons want to couple together, that's the peak of the noise. Whenever you have a resonance, you have high noise. And that frequency, as I showed, is dependent upon the photon density. The higher the photon density, the higher this relaxation peak. So what we do is we find a a quiescent point, the point at which we're going to modulate about, and then we vary the currents into two cavities such that our RIN peak here, this noise peak, doesn't vary. So hopefully you can see that all the colors here are sitting on top of each other. And what that means is that we're not changing the photon density, but we are changing the carrier concentrations in the two cavities. And so here's the bottom line, and my second to last slide. So this is showing you the output of the laser, and if I just modulate one cavity or the other, that's what the green and blue curve corresponds to. And if I look at the output, as I would expect, this is a conventional modulation of the laser. I see modulation on the output. When I do this condition where I'm extracting and injecting equal carrier concentrations in the two cavity, this is our modulation that we see out the laser. It's a little less than 3 dB. In this case, it's about 2.5 gigabit per second, which on a commercial scale, this is as slow as smoke signals. And it's really slow, but it at least shows the idea that we can do this. And so we're working now to try to come up with structures that we can actually hopefully push this out to higher rates. In many ways, this experiment relies on expensive equipment that I don't have. So that's one of the reasons why my student who's working on this is now doing a postdoc in McGill with a plant who has lots of system equipment. So what I hopefully shown you today is that in terms of first of all, there's a lot of research still to do in lasers. And simply due to the demands of the technology, that if you look at where our world is going, we need to do things better and more efficiently. And so we're trying to look at what we can do within the VCSEL world to make a better device for a better internet. And so we're looking at mode modulation approaches that decouple the rate at which the laser modulates from the power that it needs to do so. We're looking at a couple different approaches. The push-pull modulation using this rather complicated device is the one that we've developed the most, we've developed the furthest, and we've shown 2.5 gigabit per second. Spatial modulation of coherent VCSEL arrays is another approach which allows us to use coupled 2D laser arrays, which actually, when VCSELs were first pursued, coupled arrays was the first thing that people tried to do, and it was so hard that they quit doing it. So we're sort of having a renaissance here on this. And then maybe even more renaissance is that we can resurrect ideas of polarization and use that to do this. So my last slide is that I'm the one who gets to come to Mallorca and go to the conferences, but this work is done by other people. My collaborators in this work, Professor Coleman, who was also here this week, and some of his students have participated. Let's see. I didn't have his name up here. Chen is the guy who's mainly involved in this research. So with that, I thank you for your attention.
Time for a few comments or questions.
Thank you very much. I'm very fascinated by the modulation, spatial modulation by the coherently coupled VCSEL arrays. And I think it's not difficult to understand that both the in-phase and out-of-phase solutions can be stable solutions. But you showed that, I think even under continuous operating conditions, you show this modulation of the angle, which refers to intermediate angles of the locking. Is there an understanding in how far this solution can be stable?
Your surprise is my surprise. I always thought there were two modes, the in-phase and the out-of-phase. And what we've seen is there's actually a continuum. And we've actually studied this we've studied this from an experimental point of view. And you can change the phase between these two all the way up to 9 degrees out of phase. Now, I have a hard time thinking about that. How I have two lasers that are coupled together that are 9 degrees out of phase with each other. But indeed, we can see that condition in the sense that we can see what should happen to the far field, and it does. Now, if you look at the coherence of the laser, which we've also studied, because in the far field, you can look at that far field, and that's essentially a fringe pattern. And you can analyze that. And you can, with one of my colleagues, we can look at the coherence. What you find is that the coherence decreases when you get this 90 degrees out of phase. So you suffer as you move away from either the in phase or out of phase. You move away from those conditions. You suffer a little bit of the coherence. So so we're driving these oscillators in ways that they don't necessarily like. But the bottom line is they are solutions. I mean, we can see these outputs, and in terms of some of these applications where we're, for example, with beam steering, the coherence is not really not that relevant. So it's interesting. I will write some papers, but in this application, it looks like I can drive it. But I will admit that in terms of solving this problem. All I've seen are the in phase and the out of phase, but experimentally we see everything in between.
Did you talk about beam steering or locked array, basically modulating the in phase to the out phase? And you said it should be fast, but what are the limiting factors and fast how?
Okay, so now I really should throw in some more vigorous on that. What we've done is we've tried to identify the mechanism, and I mentioned that we believe that we're injecting carriers and doing a carrier-induced change in refractive index. When we look at this beam steering as a function of we really can't. We haven't built devices where we can do things dynamically, but when we look at, we can pulse the laser. And we look at compared to CW versus pulse, what we find is it's not a thermal effect. It's not due to changes of temperature, which then would give you a change in refractive index, that it indeed seems to be electronic in origin. And if it's electronic, then in principle, it's as fast as we can get the carriers in and out of the cavities, which is an engineering problem. It's like then that's related to the capacitance, the resistance, things that they're challenges, but we know how to attack those problems. And which is what we're doing is we're trying to build these coupled arrays in a high-speed configuration where we can modulate them. The more interesting question is that ultimately it's related to the carrier lifetime. The photon lifetime. But this is a coupled mode. So again, in this regime where we're not in or out of phase, we're somewhere in between, and the photon lifetime, it's kind of an open question in terms of what the ultimate limitations are.
But basically you have to move carriers from one place to another place.
Yes.
So it's a capacity.
That's right. And the hope, as I showed them when I showed the data, 1 milliamp of current was what I was using to vary over 6 degrees, which is enough to steer on off a detector with suitable offset. And typically in a VCSEL, in an actual system, usually you have 5 or 6 milliamps of drive current that you're switching. So we're lower than what's typically used. And so again, so we're maybe not exactly at this condition of constant photon density. Although what I should say is, if we inject the same carriers into one and extract out the other, then we can keep a constant bias current. But to that extent, it's independent of the total photon density.
The total photon density should remain the same, we just displace locally the charge.
Yes. And through that change the index, and through that change the cavity, and then through that change the boundary conditions of maximum equations, which change the output.
I have a remark. So the remark is about the solution with an arbitrary phase. If one has two oscillators which are different, which have different frequencies, and they work together.
Different frequencies.
Two oscillators with different frequencies that work together. When they work, the phase difference depends. The phase between them depends on the difference in the natural frequencies and the coupling. So, So two different oscillators work together are not in phase, are close to in phase if the coupling is strong. But if you decrease the coupling, they work together, they have the same frequency, but the difference in phase increases with the difference in the natural frequencies or reducing the coupling. And that might be the case why you see solutions. If you change the conditions, you see solutions with different frequencies between them.
It's a continuous mode.
Well,
And also separated.
If you change continuously, it changes continuously.
Yeah, it is continuous.
If you change continuously the frequency of one of the elements, then the frequency, the phase at which between them or both of them when they are work changes.
So at least to first order, the two oscillators are at the same frequency.
Yeah, but
Because-
I mean, they must be very close one, because if not, they do not work. But once, I mean, that's the first thought, but then there might be still some slight frequency difference which determines the precise phase difference that you get.
All right.
The bare frequency.
And also in that analysis is buried coherence.
Yeah.
When you look at the coherence, you can say something about how close the frequencies are. So we started to try to analyze this line width. This is because to the degree to which the two oscillators have different frequency should be reflected there. Now this is experimental limited, so we need to do this in much
So
more.
for example, a way to test that, if you have a way to increase the coupling between the two, then the phase difference should decrease.
Yes.
But of course, that's very theoretical and experimental,
Yes.
very difficult.
Well, but we actually have a handle on that because we can change the coupling, because the way that it's hard to see this, but the way this coupling between the elements is manifested in these devices is by changing this the hole. Now I can't tell you that we have a calibration between what we fabricate and what the coupling is, and that's something we're working on, trying to understand the coupling. And in fact, we have a paper that was just accepted in Choquette on. We used couple load theory and to analyze this problem, and then we brought in coherence into that problem. But I will admit that in that analysis, I think we fixed the frequencies. But there's a lot of I've read a lot of papers that have analyzed similar problems. It's just I'm not certain yet if how coupled we are. At least to the experimental data they have right now says that these two oscillators are locked together.
No, sure. I mean, they are work together. They have exactly the same frequency. But since the natural frequency was different, the phase difference reflects the difference in natural frequency.
But the natural frequencies, at least to the
ones that are coupling from the coupled system.
right. Well, the natural frequencies should be identical because it's the same device. It's only a few microns away from each other.
That's right, but they might be different in megahertz.
Granted.
Or even
Right.
gigahertz.
Yes.
And that's okay. That's what
maybe
I'm talking about. A small difference in there, which then, when they work together, imply difference in the phase. That's what I'm talking. I'm not talking about difference in frequencies which are huge. Then they will not work together.
Okay. We're not sensitive to anything.
It's a tiny balance, basically.
Okay.
We can discuss that.
Yes, that's it.
And then the question is about when you write down the rate equations, you show that in your system, in fact, there are sort of two modes for the electromagnetic field. In fact, one the peak is centered at one of the cavities, and the other one that the peak is centered at the other cavity.
Yes.
Typically, one would consider that the way to model when there are modes, when there are longitudinal modes, for example, of the carriers or of the population, or modes of the electromagnetic field, one can consider, for example, two modes for the electromagnetic field, projecting the electromagnetic field onto the distribution of carriers. So then you would get four equations, two for the carrier population and two for the two electromagnetic field modes, which one is the one, say, on the top, and the other mode is the other. And then you have competition between these two amplitudes. And that might give you a different response, and you might avoid having this flat response that
Yes.
you don't get anything.
Yes.
And with that will complicate a little bit the model, but it will still be a very crude and simple model that might provide some some better approximation to this.
One comment, though, to make sure that I don't want to mislead you, is that one or the other, this is one mode. There's actually another longitudinal mode, because we have two oscillators and they're coupled together, so the degeneracy is split. So we have two longitudinal modes that are split by, in this case, by 8 or 9 nanometers. And what we're doing is we're just looking at one of those modes, and then this is that mode in these two different configurations. So the whole problem is actually four modes.
Yeah.
Yeah.
But even if you look at that mode, since there are two possible configurations, and the rate equation has no way to cover the spatial dependence of this mode.
Right.
The way to put that on the rate equations is like two modes with the
Yes.
same frequency.
Yes.
One corresponding to the absolution
Yep.
and the other
And-
somehow.
Yep, and what is that? Oh, yeah, and we assume one mode in our rate equation. And,
That's what
yep,
it should be
yep.
4 equations. And,
Yeah.
and of course, if you have those other modes which might play a role, then you.
That's the next student.
Yeah.
Okay, maybe we should continue to the schedule. Yes, there were another couple of questions. Schedule against
No, no, it's fine, it's fine. No, I can talk to him.
the end of you. So let's send the speaker again.